Okay, here we go with polyatomic ions and shapes of molecules in polyatomic ions. Last time we put together compounds that did not have charges. Now remember, charges are either adding or subtracting electrons. So right here on the first I've put SO4 with a 2-. Notice that we would arrange normally. Sulfur has 6, those are represented by the blue. Oxygen each has 6 also. But when we go to put them together so that every one has 8 electrons, we end up being short on a couple of them by 1. So this one and this one are short by 1. You can see that by the black one that I've put in. The other two have enough, but these two need 1 more each. That's where the 2 comes from, because I had to add 2 electrons. So this is a group, or gang as I called it in class, remember gangs are negative, that needed 2 more electrons. The theory that puts everything together as far as 8 electrons in the outer octet and the shape that they're going to be doing is called the vesper theory. And I'll be talking about that on and off, but if I ask you to draw something according to vesper, it's just put them in where they have 8 electrons around each atom. Now that it works all except for helium and hydrogen, which only need 2. Okay, now here is the diagram for NO3, which is nitrate, and we've been using that a lot in naming formulas and going back and forth. And nitrate has a -1. Now if I go to put it together, I can get 8 around this oxygen, no problem. I can get 8 around this one by doing a double bond with the nitrogen. But then this oxygen right here has 1 more that it needs right here. And so that's why I add 1 electron, and that's where the negative comes from. Okay? Now I can also draw the nitrate ion like this. Remember that a line represents 2 electrons, so I could have it drawn like this. I still added that other electron in there, and some diagrams that you will see will not have these extra electrons around them showing that they're there. They'll actually just show it like this, where they have the nitrogen hooked up to an oxygen, hooked up to an oxygen, hooked up to an oxygen, and then they'll put it in brackets with a minus on the outside. They won't show the electrons around the oxygen. I like to do that because I like to be able to count that there are 8 there. And you'll see them in more advanced books, but sometimes they just drop those off. And in your book, as they show you sometimes, and it does get messy, it's assumed to have 8 around it unless you show otherwise, or unless there's an unshared pair of electrons that you do need to show on the main atom. Okay, so here's one that has 3 H2PO4, that's dihydrogen phosphate, and you'll notice as we arrange everything out, we've got the oxygens, 1 on each side of the phosphorus, and then we've added a hydrogen on the right and the left to fulfill oxygen's requirement of 8. Phosphorus has its 8 around the center, and then we have this 1 oxygen right here that needs an extra electron, and that's where we get the -1 charge. Now remember, you can also draw it like this. Now the hydrogens actually come in and out of the plane, so they're not actually attached to this lower oxygen down here or close to it. They're actually coming out at the plane or into the plane from this area. So I wanted to make sure that I redrew it and sort of explain that. But again, it has a -1 charge. Okay, this is ammonium. Remember, we had our 2 positive ions or positive gangs that we need to remember. One was ammonium and one was mercury 1. Remember, mercury 1 is Hg2 with a +2 charge. So redoing ammonium here, we get nitrogen in the center, that's the blue, and then hydrogen comes in with its 1, and notice this hydrogen up here gave up its electron and just hooked onto both of nitrogens here. So because it gave up an electron, so an electron has gone away, that's where we get the plus charge, because we've got 1 extra proton in the center. Now you could draw it like the one on the right also. Why?
Never mind. So I was asking this girl where she went to high school, and she says, well, I'm still at ATM. I was like, where the heck is that? You know what it means? At the moment. So she's still in high school. That's awkward. That's weird. I don't know. Oh, she's got a big nose.
You're so kind.
Well, I didn't know I was kissing her.
Wow.
Wow.
Okay, so here's sulfite, SO3 2-, and the black around the sulfur on the left is its original electrons. And then as I go and I put the oxygens around it, I've got 2 electrons here that I need to add in. So an electron here and an electron here. And that 2 electrons is where that -2 came from. Now again, I can write it like the one on the right, or I could write it like this. And that's sometimes how they write it without the electrons around the oxygen, but around the center atom you do need to show them.
Alright, time to go. I'm sure I got it right. Back to the garage for me.
Okay, so here we go with phosphate. Phosphate again, phosphorus has 5 around, that's the blue. Oxygen each has 6 around. And this time, as I put the oxygens around, I end up having to put an extra electron at each oxygen. And because I have to put one at each oxygen, that gives me 1, 2, 3, and that's where the -3 came from. So again, without showing the colors, I could do it like this, or phosphorus with oxygen, 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 and a -3, or 3 negative. Now up to this point we basically talked about doing Lewis diagrams and how to put the electrons around each atom. But you need to know what shape that will actually take in a 3D sense. So if I have 2 things attached, it's like having 2 balloons. You're going to get a line, a linear. This angle right here, from here to here, is going to be 180 degrees. If I have 3 things attached, like the next thing down, I actually am still in, we call, basically this is one-dimensional. We get 2-dimensional, which we start to make a plane. So if I had 3 balloons attached, they would lie in a plane. Okay, and the angle here is my 120. Now if I have 4 balloons attached, and this gets a little tricky here because you got to see this balloon coming out at us, then I get this shape right here, and the angle right there is 109.5. I've got it written up above her, so it's probably not, don't need to write it there. So you got to sort of look at this. The black area right here is going back into the plane. This one is coming out at us. So it's a 3D molecule. Okay, so we call that tetrahedral. The one with the 3 we call trigonal planar, so it's sort of like a triangle, but it's in a plane. Okay, and I did give you a sheet on the back of your mole map that goes through each of the different kinds of shapes of molecules and sort of has them drawn for you, so you might want to look at that. So this is SO2. SO2 is not a polyatomic ion, it's just a compound, and it's a molecular compound. So we'd name it sulfur dioxide because it doesn't have a charge. So on this one, when we put together the Lewis dot diagram, you can see the blues are sulfur and the reds are oxygen. I don't have to add any extras, but I do have to share these two in a bond and these two in a bond to the same oxygen. So we have a double bond. So if I rewrite it like this one over here, then you can sort of see it a little bit better with the 2 lines drawn as the double bond, a single line for a single bond. Now I've done the yellow around it so you can sort of see it's like 3 balloons, or 3 things around the central atom. And that's what you want to remember. Even unshared pairs of electrons can be a balloon around the central atom. If you think of it that way, then it's really easy to see the shape. You can see that there's 3 balloons, so it's trigonal or triangle planar, and it's 120 degrees for the angle. Okay, so as we look at the molecule C2H4, which is also known as ethene, but you don't need to know that, we can see that carbon would have 4 around it, and if we have 4 hydrogens, then if we put 2 hydrogens on each carbon to make it even, then carbon still needs 2 more each, so they will have to share 2 in between them. So redrawing this, I would have carbon double bound to carbon, and remember we want to go equal places away from each bond because they force each other as far apart as they possibly can. There's 2 other things coming off, so we're going to go at an angle like this, so it's going to be 120, and I'm going to have a hydrogen coming off here and a hydrogen coming off here, a hydrogen here, and a hydrogen here. Whenever I have a double bond, it is going to force the molecule to lie in a 2-dimensional plane. Okay, so this is going to be in a plane. We don't have a specific name for this kind of drawing, but let me go and put it into a drawing where you can see with just shapes like we would make in lab with our Tinker Toys that we've been playing with, or will play with if we haven't. So here's the carbon. Carbons are black, and we'll say purple is hydrogen, because it usually is white, but white won't show on white. And then if we connect the bonds, we've got a double bond between these 2, and a single bond here and here and here and here. So that's what the molecule would look like. Now you need to be able to take a Lewis dot diagram and decide how it's going to arrange so that around each molecule or each atom there are 8 electrons with the exception of hydrogen and helium. So here, remember, each line represents 2 electrons, so we go 2, 4, 6, 8, and 2, 4, 6, 8 around each carbon. Alright, that takes us through, for the most part, up through the end of 4.8. Now I know there's a lot more shape stuff in there, and hopefully we'll cover a little bit more in class. But make sure you look through that and sort of see how they're doing it. They can do the shaded diagrams and that a little bit better than I can without. And we'll see you in class.